Hello everyone, in this video I will show you how to build your own GPT. And before that, we need to understand how large language models work. And with large language models, we have inputs, and these inputs are text. So they're gonna get transformed to numbers through a process called tokenization. And then these tokens, which are now numbers, are gonna get transformed through passage, through self-attention, and feed-forward layers in our network. And I'm going to explain these later in the video. And then that's going to lead to output generation, because the way large language models work, they just predict the next token in the sequence. Let's say you are a large language model and you want to basically create the following two lines of text. The way you work is that first you have P, and then given P, you predict R, and then given P and R, you predict E, and so on and so forth. And at the end, you come up with the text, and that's how we want to generate our output. And then we're going to detokenize the output, because at the moment, our output is numbers, but we want to go from numbers to letters again, so we can read them, and that's going to be the response. With this in mind, let's go through the code to see how we can create a large language model such as ChatGPT from scratch. If you like this video, please don't forget to like and subscribe. First things first, we need to download our dataset. And for this example, I'm gonna use a tiny Shakespeare dataset, and we're gonna download this dataset. And before moving forward, let me thank Andrei Karpathy, because the code we are using right now was originally written by him. So I want to thank him for the code. So after that, we download our data set. And as you can see, these are the first 10,000 characters within our data set. It's a very normal Shakespeare text. And right now, I want to basically store all of these characters into a variable called cars, right? So these are all of our characters in the data set. So I'm gonna do that using this line of code, and then we are gonna get all of these characters. So these are all the characters in our data set, and we have a total of 65 characters, and 65 includes the space character at the beginning. So we have all these characters in our data set, and they're now stored in this variable. So the next thing we want to do is that we want to basically tokenize these characters, because right now there are letters and computers do not understand letters. And the first thing we have is stoi. So stoi means a string to integer. So basically we want to transform these strings into integers, and then we have itos, integers to strings, and that's for the tokenization. So basically we go from numbers to strings. So if you look at the following example, hider, when it gets encoded, we have the following numbers. And basically we have 9 numbers, because yes, we have 8 letters, but we also have a space. So we have a total of 9 basically numbers. And if we decode this, we are gonna get this. So that's how basically tokenization works. And this is a very simple example. You can become fancier too, but for our example, this works. So in order to work with neural networks, we need to basically transform this data into tensors. So if you don't know what are tensors, tensors are basically a format that enable GPUs to do parallel processing, and parallel processing is what makes GPUs beautiful. So it's okay if you don't understand them, but understand that right now we are just transforming our data set from its current format into a tensor that's gonna be later used in our model. So we do that, and then we come here, and basically here we are splitting our data set into 2 parts. We have the training part and we have the validation part. So 90% of our data is going to be training. So that data is going to be used for the training, but The other 10% is going to be for validation, and our model is never going to get trained on the validation data, because when it comes to validation, we want to see how our model performs, and if our model is familiar with basically our validation data set, that undermines the whole purpose of validation. So that's it. And in the second chunk, we are basically defining our block size. So in each block, we are having 8 characters. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And as you can see, we have a +1 here, so it's going to be 9. But I'm going to explain why later. So we have the block size, and the block size is basically our x, is our input to the model. And here we have a y data, and as you can see, the y data has a +1, because as I mentioned earlier in the video, we want to predict the next token. So this is our initial set of tokens, and when we do +1, our y basically set is always 1 token ahead of our x. So we are always trying to predict our y's using our x. For instance, let's say we have 18, and using 18, we are gonna have 47 as our target. So when x is 18, y is 47, and when the x is 18 and 47, our y, our target, is 1 step ahead. So we have 56 as our target, and so on and so forth. So that's why we have a +1 here, because we always want to make sure our y data is 1 token ahead, so that we are predicting the next token. So that's it for the tokenization. And then in this part, we want to basically transform our data into a format that can be understandable by basically torque. So basically, we want to define our batch size and our block size, because we can never feed all these data into our model for training. That's not how it works. Instead, we split the data among batches. So batches are independent sequences that can be processed in parallel. As we mentioned before, GPUs enable parallel processing. So when I say my batch size is 4, it means that we are gonna process 4 independent sequences all at once, and the block size is 8, and that means each block within our batch has 8 sequences. So we're going to apply that across our data set, and that's what we come up with. So as we can see, we have 1, 2, 3, 4 batches, and each batch has 1, 2, 3, 4, 5, 6, 7, and 8 basically tokens. And these are our inputs, right? These are our X data. But as you remember, our Y data is 1 step ahead, and that's what enables prediction. So as you can see here we have 24, but we have 43 here, which is 1 step ahead. And here we have 24, 43, and we have 58 here, which is again 1 step ahead. So our X data and Y data look similar in terms of a structure, but our Y data is just 1 step ahead of our X data. And we have the same format as we had before. So I'm just gonna skip through this. And here we are basically designing our first model, but this time it's just for the sake of explanation. We are gonna do it later in the video, but just bear with me for a second. And right now, the first thing we are gonna do is that we are gonna design a bigram language model, and we are basically creating a lookup table. And this lookup table, the dimensions are vocab size by vocab size. So let's say we have 64 vocabs in our data set. So we have 64 rows and we have 64 columns. And in each row, we have a, let's say, vocab, and the data within our basically table is a logit, and logit basically tells us the probability of having a certain next token given the current token, which is our row. So let's say in our row we have the letter A, and basically we have that same letters on our column. So maybe there is a 50% chance that the next letter is gonna be A. Maybe it's 50% chance that's gonna be B, and the probabilities are the data within the lookup table. But it's important to understand that we are not using probabilities yet. We are using logits, and logits are gonna get transformed into probabilities once we use something called softmax. But for right now, just understand that on a general level, we are creating a lookup table that has letters on both rows and columns, and at the intersection of each, we have the probability of having the letter on that column given the previous letter is the letter on the row. So it's complex, but it's gonna make sense later in the video. And here we are basically trying to do the prediction, and the prediction here is not going to make sense because we are not training the data. But here we have something important I want to talk about, and that's basically loss. So as I mentioned, we have logits in our data set, in our table, in our lookup table, and this function, the cross entropy, is gonna turn those logits into probabilities, and we are gonna basically compare our predictions with targets, and that's gonna be our basically loss. And loss is how much how wrong is our answer. So the larger the loss, the more wrong our answer is. So it's all gonna make sense later in the video, but just for the sake of explanation, B is the batch size, T is the sequence size. So for instance, here we have, I don't know how many batches we had, but let's say we had 4 batches, and T is a sequence number. So we had 8 sequences, and C is the number of features that each token can have. And in our case, it was 65. And these are our logits, and targets are similar too, but it's gonna make more sense in the video once we dive deeper into them. So right now we are also doing the generation. So as we touched upon earlier, once we have a token, our job is to basically understand what's going to be the next token, and here we are doing that by using the lookup table. So when we have, let's say, letter A, our job is to understand, okay, what's likely to come after this particular letter based on our lookup table. And that's how the generation works. And in order to do the generation, we need to have the starting point, and usually the starting point is a new line character, and from there the generation is gonna get initiated. And as you can see, this is our current generation, which does not make sense at all because it's just random. We didn't do any training, but hopefully this taught you how these models work under the hood. All we are doing is predicting what basically token is gonna come given what tokens we already have in our sequence. Okay, so but if we want to train this model, we want to use something called optimizer, and optimizer is responsible for something very important called backpropagation. And to explain backpropagation, let me give you an analogy. Let's say you touch a hot stove, and you're gonna get punished for that because it's gonna hurt. So you're gonna remove your hand, and next time you see a stove, you're not gonna touch it because you learned that it's gonna be painful. And that's kind of similar to backpropagation. So you do something, you either understand that it was a good thing to do or it was not a good thing to do, and based on that understanding, next time you're gonna pursue a different course of action, or if it was a rewarding path, you're going to pursue the same path. But nevertheless, going back and doing something different or same thing is called backpropagation, and that's how learning happens under the hood. So here we actually want to train the model. So basically we didn't train our model when we ran this part of the code, but here we want to train the model, and we are going to use this optimizer, and the learning rate is going to be the following. And basically we are going to update the weights of our model using this optimizer, and the optimizer we are using is Adam W. And as you can see, once we do that, the loss is going to be the following, and this loss is huge. We can definitely reduce it, but this is the output of our model after we incorporated the optimizer into our code. And as you can see, it still does not make any sense. So in order to improve that, we need to use something called self-attention. And self-attention is the way tokens in our sequence communicate with one another. So let's say we want to predict the next token in our sequence, and we cannot do that by just taking the last token into consideration. We need to look at all of our tokens, and we need to basically come up with the next token given a good understanding of all the tokens that came previously. And that's how we can make a more informed decision. And in this code, I basically have a very simplified way of looking at basically self-attention. So let's say this is the first token in our sequence, and so let's say we want to predict the next tokens given the tokens we already have. And right now, because we only have one token, it's only gonna be considered when it comes to generating the output. But if we have two tokens, then both of those tokens are gonna get considered when generating the output. So the last token is gonna have a weight of 0.5, and the first token is gonna have a weight of 0.5. So in this case, we have equal weights when it comes to predicting the next token. And let's say we have 3 tokens in our sequence, and then when it comes to predicting the next token, we're gonna give all the tokens in our sequence equal weight. And you can see the problem with this approach, because if we're assigning all the tokens we have equal weights, then that's not gonna be helpful, because some of our tokens are just more useful than other tokens when it comes to prediction. So we cannot assign them with equal weights. And this is a good way to understand self-attention, but that's not how self-attention works in the real world. And here we also have another example of how self-attention should work. This is the same. Basically, we are going to assign equal weight to all the tokens in our sequence when it comes to predicting the next token in our sequence. And this is just a more vectorized way of doing what we did here, which is more appropriate when it comes to large language models and training them. But the problem is still the fact that we are basically averaging the weight across all the tokens we have, and it's not helpful because they should not have equal weights. And the next version I have here utilizes softmax and masking to do the same thing, and still we are not basically updating our weights properly. We are not learning in a sense. But in the third approach, we are doing 2 things that are very important. First of all is the incorporation of softmax, and the second is the incorporation of masking, because when eventually we want to train our self-attention, we want to use softmax, and we want to use basically masking. And softmax basically takes our logits, and it's gonna transform them into probabilities. So the larger the logit, the higher the probability, and softmax is gonna just turn the logits into probabilities. And also, because we are training our model in a text sequence, we want to make sure that the future sequences in our data set are masked, so that basically our model cannot look into them when it comes to making predictions. So this third version is not helpful, but we are incorporating softmax and also masking, which are very important when it comes to actually doing self-attention. And in the fourth version, we actually do the self-attention. So basically, I'm setting a manual seed, and manual seed helps us come up with the same model response whenever we run this model. So I'm just going to set the manual seed, and also I'm going to come up with my BTC. So B is the batch size. I want to have a batch size of 4, and 8 is our sequence number. So we want to have 8 tokens in our sequence, and C is the number of features per token, and we want to have 32 of them. So here we are defining our head size, and I'm going to explain head size later in the video, but head size basically makes our self-attention mechanism more robust. And there are 3 things that are very important in any self-attention mechanism, and these are key, query, and value. So key is basically the response and the information all the tokens have, and the query is basically the question all the tokens have. So let's say I'm a token in a sequence, and my question is what information other tokens in the sequence have that I can use. And basically the key is the response to that query. So let's say I'm a token in a sequence, and the key is my response to this question, and basically the value is what gets transferred. So if I'm a token and I decide to pay attention to another token in the sequence, the value is what I'm gonna get out of that token. So here we are basically measuring our weights using our K and Q, and next we wanna train these K, Q, and V, and that's how the learning happens. So similar to backpropagation, that's how we update our basically self-attention weights. Each time we do the trainings, the key, the query, and the value get updated, and they help us basically assign a more proper weight to each token within our sequence. And learning doesn't happen here because we are not actually training, but later in the video we're going to actually train our self-attention mechanism. And self-attention mechanism is just a way for our tokens in a data set to basically communicate with each other. And now that we understand self-attention, I believe it's a good time to just go through the entire code to generate our GPT. And we are doing the same thing we did before. We are importing our torque and the necessary tools. We are setting our batch size to be 16, the block size to be 32. So we are gonna basically analyze 16 sequences simultaneously, and we are gonna have 5,000 iterations during our training, and we are gonna have 100 training rounds before we do an evaluation. So evaluation is basically testing our model, and the learning rate is the following. And here we are gonna use GPU if we have access to GPU, but if we do not have access to GPU, we are gonna use a CPU. And basically each time we are evaluating our model, we are gonna grab 200 basically batches, and we are gonna average their loss to see how are we doing. And the number of embedding is the number of features each one of our tokens can have, and the number of head is 4. And I mentioned that I'm gonna explain the head number before. And basically when we have a self-attention mechanism, we have the key, we have the query, and we have the value. And when we have multiple heads, multiple self-attention heads, we can ask multiple questions. So instead of having just one query per token, we can have multiple queries, and hence we can have multiple keys. And that's gonna make our self-attention mechanism more robust. And this is the number of layers within our neural network. And also we have our dropout. So dropout is a measure to avoid overfitting. So basically, using dropout, we are gonna deactivate a certain number of our neurons during the training, and that's gonna help with the generalizability. If you wanna learn more about dropout, you can read more about it, but I'm not gonna overcomplicate this video. And similar to what we did before, we are going to import our data set, we are going to do the tokenization, and we are going to come up with our train and test splits. We are going to come up with our batches and our basic sequences. And here we are basically evaluating our loss before doing the training. And you can see that we are not doing the training because our weights are not going to get updated. Basically, using this line in torque enables us to not update our weights. So basically, when we are evaluating our loss here, we are not going to update the weights. We just want to see how our model is doing. So in here, we are basically defining our head, one of our self-attention heads. We have the key, we have the query, and as you can see, right now they can get trained, and that's what we are doing. We are training them, and we are basically measuring the weights here. And this is basically the same thing we did before, but this time we are doing it with the multi-head attention. So as you saw before, we have 4 heads in our self-attention mechanism. So this is basically the same thing but applied to 4 heads. And here we have the feed forward class. And in order to understand feed forward, we need to expand on our understanding of self-attention mechanism. So self-attention mechanism is a communication between the tokens in our sequence, but feed forward is computation within each token. So each token has certain features, and we are interested in those two. We want to transform those two, and the feed forward is gonna basically update those. It's basically gonna do those within token computations. So self-attention is between tokens, feed forward is computation within the tokens. And once we do that, we are gonna define our transformer block, which is the addition of what we have already covered. So then we are gonna come with our bigram language model. As you remember, we did that previously, but at that time we were not training our model. But this time we are really training our model, and we are doing the same things. We are doing the embeddings, we are doing the predictions, but the only thing that we haven't covered is normalization. So we do normalization to make sure each feature that our tokens have the mean of 0 and variance of 0. That's the purpose of normalization. There is not much to it. Just add it to your neural networks when you're doing your GPTs, and that's basically it. We compute the loss, we come up with our logits, we compute the loss, and then we do the generation the same way we did before. We start from a new line character and basically start the generation from there. And as you can see here, we have our training and validation information, and as you can see, our final training loss is 1.6, almost 1.7, and compared to what we had earlier, which was, I don't know, 4.2, 4.5, this is much better. And you can see that self-attention mechanism and optimization, they all work. So this is the final output of our model. As you can see, it has a structure. It has a structure you would see in Little Shakespeare. And some of the words make sense. So bot makes sense, userman makes sense, this, that, where can I, is, not, dynasty, rich, So I don't really understand it, but as you can see, we are starting to see some trends that make sense. And that's the final generation, but you can see that this is not the same as ChatGPT, because once you use this model, the way it works, even if you ask a question, it's not going to answer your question. It's basically going to continue your prompt. So if you ask a question, it's basically just going to maybe ask more questions that are not even relevant. It's basically just going to autocomplete your query, and it's not going to respond to your question. And that's because we have only accomplished the first part of training any GPT or any large language models. So when we are training things like ChatGPT, there are two parts. The first part is pre-training, and pre-training is what we did here. But the second part is fine-tuning, and fine-tuning is when we get this model and we try to give it some structure, we try to give it some guidelines to answer questions. And if we go to OpenAI's website, you can see that it defines fine-tuning as providing examples of correct responses to prompts to guide the model's behavior. So let's say we ask a question and our model just comes up with some generations, and we want to rate those generations until our model understands what's the correct output given our prompt. And there are multiple ways to fine tune. We can come up with reward systems. So we're going to reward our model when it generates a good response. There are many ways to do it. I did not cover this part in the video because OpenAI does not share those information, and I didn't want to overcomplicate this video. But in order to create something like ChatGPT, you need to have the fine-tuning part as well as the pre-training part. That's it for this video. If you liked it, please don't forget to like and subscribe. If you have any questions, please leave them in the comment sections. Thank you very much.